A model is the core component of an artificial intelligence system. It is a mathematical structure that maps inputs to outputs based on learned patterns. Understanding what a model is provides clarity about how AI systems operate and what they can realistically achieve. Models differ fundamentally from traditional software programs. Instead of following explicit instructions written by developers, models behave according to parameters learned from data. This distinction explains why AI systems can adapt without being manually reprogrammed. Models exist because many real-world problems are too complex for explicit rules. Learning from data allows systems to capture patterns that are difficult to formalize using traditional programming approaches. Early AI relied heavily on rule-based systems. Models represent a shift away from hand-coded logic towards statistical learning, where behavior emerges from data rather than predefined rules. A model represents relationships between variables in mathematical form. It does not store facts or concepts. Instead, it encodes associations that allow predictions or classifications to be generated from inputs. Models are often compared to brains, but this analogy is misleading. Models do not think, reason, or understand. They apply learned mathematical transformations to data. At a basic level, a model takes inputs and produces outputs. Inputs are structured features, and outputs are predictions, classifications, or numerical estimates. Features serve as the model's input language. The model has no access to raw reality, only to the structured representations provided through features. Outputs represent the model's best estimate given its training. These outputs are not certainties, but probabilistic or approximate results based on learned patterns. Models learn statistical relationships within data. They identify correlations, trends, and regularities, not causes or explanations. Learning occurs through adjustment. During training, a model modifies internal values to reduce error when comparing predictions to known outcomes. These internal values are called parameters. Parameters determine how strongly different inputs influence outputs and collectively define model behavior. Changing parameters changes how the model responds. Learning is the process of finding parameter values that perform well on the training task. Models vary in complexity. Some have few parameters and limited flexibility, while others have millions or billions of parameters and high expressive power. Model capacity refers to how complex a pattern a model can learn. Higher capacity allows richer representations, but increases risk of overfitting. Overfitting occurs when a model learns noise instead of general patterns. It performs well on training data but poorly on new, unseen data. Underfitting occurs when a model is too simple to capture meaningful structure. It performs poorly even on training data. Effective modeling requires balance. The goal is generalization, meaning good performance on new data rather than memorization of examples. Training is the process through which models learn. They are exposed to examples and gradually adjust parameters to improve performance. Loss functions quantify error. They provide a numeric measure of how far predictions deviate from desired outputs. Optimization algorithms adjust parameters to minimize loss. This process is iterative and continues until performance stabilizes or improves sufficiently. Learning occurs over many iterations. Each step makes small adjustments, gradually improving predictions rather than achieving instant accuracy. Training data defines what the model can learn. If patterns are absent from data, the model cannot infer them. Validation data helps monitor learning progress. It provides feedback on generalization during training. Testing data is used only after training. It provides an unbiased estimate of real-world performance. Models do not reason or understand context. They operate entirely within the mathematical space defined by features and parameters. Correlation does not imply causation. Models detect associations, which may not reflect underlying causes. Models are context-bound. Applying them outside their training conditions can lead to unreliable results. Models reflect the data they are trained on. Any bias, imbalance, or omission in data becomes part of model behavior. Bias often enters systems through models. Learned patterns can reinforce existing disparities if not carefully managed. Some models are more interpretable than others. Simpler models allow clearer explanations of how inputs influence outputs. More complex models often offer higher accuracy, but reduce transparency. This trade-off complicates trust and accountability. The term black box describes models whose internal reasoning is difficult to explain. This poses challenges in sensitive applications. Model size affects performance, cost, and interpretability. Larger models require more data, computing resources, and oversight. Performance metrics measure accuracy, but reliability also matters. A model can be accurate yet unreliable in edge cases. When deployed, models interact with real-world systems. Errors can have tangible consequences beyond technical evaluation. Model drift occurs when real-world conditions change. Over time, performance may degrade if models are not updated. Monitoring helps detect drift and failure. Continuous evaluation is essential for responsible deployment. Updating models may require retraining with new data. Models are not static artifacts but evolving components. Viewing models as part of a life cycle helps prevent misuse. Design, training, deployment, and monitoring are interconnected stages. Human oversight remains essential. Models assist decision-making but should not replace accountability. Trust in AI depends on trust in models. Transparency, validation, and oversight support confidence in outputs. A common misconception is that models are intelligent agents. In reality, they are tools that apply learned patterns. Models do not understand meaning. They manipulate symbols based on statistical relationships, not comprehension. Models matter because they define system behavior. Choosing or designing a model shapes outcomes directly. Selecting the right model depends on the problem, data, and constraints. There is no universally best model. Models have limits. Recognizing these limits helps prevent overconfidence and misuse. Responsible use requires aligning model capabilities with appropriate tasks and maintaining human oversight. The key takeaway is that models learn patterns from data, not understanding of the world. Next, we will examine the difference between training and inference, clarifying how models are built and how they are used.